That wasn't me. Could you please silence your phone? We're being recorded now. Okay. Matt.
Mateusz Lowiel from the University of Warsaw. He's here in Western Sydney for 3 months almost, and he's going to tell us a crash course on classical representation theory of path algebras. Mateusz, please.
Yeah, beforehand. It was kind of loud.
Are you going to get money for exercise?
And the appropriate body that handles all of graph algebra money knows it's bigger than any hedge fund known to humanity.
So
Okay, so I presume I can start. So yeah, I'd like to, of course, thank everybody that was involved in the organization of like this event and like my whole trip here. So, I mean, it's a thank you essentially to everybody that's gathered here. And yes, I'd like to thank you for that. And today I'll be talking about a very classical theory, and I think it's, I hope I won't bore you to death because I will be talking about finite dimensional objects and finite dimensional stuff. And, as far as I know,
and these dimensions will be big, like 100.
I mean, it might be arbitrary. It might be any arbitrary dimension. So if you really like big dimensions, then yeah, you can think about very large dimensional objects. But yeah, so I'll be talking about the classical representation theory of path algebras, and as they may be, oh no, wait, the arrows aren't working. That's, how do you change the slides? Yeah, I mean, oh, okay, okay, I will just use this. Yeah, so I actually presume that everybody had the time to read this part. It's just a very simple introduction. So yeah, I will mainly focus with finite dimensional modules, and I actually will be also mainly focused with finite dimensional algebras. And yeah, so this is a very like classical stuff, and people, I mean, nowadays people are usually concerned with like more infinite dimensional stuff. So like I don't know, for example, I was reading some papers on the geometry of representation of an infinite dimensional algebra that's just a cyclic algebra, a cyclic quiver, and we make the path algebra is infinite dimensional. And you can try to do some representation theory of that, and most of these tools fail in this infinite dimensional setting. So that's just like a little spoiler. I won't be talking about infinite dimensional stuff, but I presume that other people today will be talking about some representations of some algebras that are path algebras and that are not finite dimensional. So yeah, let me go for the plan of the talk. And the plan is, as you can see, threefold. Although the third point is actually cut a little short because I'm kind of bounded by the time I have for this talk. So I will be just doing, I mean, I want to lay out the notation and like some properties of quiver representations. And then I want to talk about, like, for me, what was the more interesting stuff when learning this theory. And this is the kind of Auslander-Reiten theory, which is a very kind of, I don't know, almost algorithmic way to kind of compute the whole category of modules of some, well, of bounded quiver representations. And yeah, so the last part is about the larger results. So for example, the Gabriel's theorem, which I think is a necessity to state in a talk like this. Although I, of course, will not be proving this theorem during the talk because I only have so much time. So yeah, let me maybe get started because we don't have that much time. And I also want to put my phone here to know how much time I have. Yeah, but I don't really see the clock. So Yeah, so very like to start things off, I'll be working with some algebraically closed field. If you're uncomfortable with any algebraically closed field, you can just think about C and nothing, literally nothing that I will be talking in here changes. Like the field should be algebraically closed, and that's it. All modules will be right modules for me. And if you are also uncomfortable with that, then you can reverse all arrows in all quivers that I will be defining, and then you can consider left modules, and the theory is essentially, I mean, it is the same. So that's the second part, and a small definition is about radicals. So I will be talking about radicals at many different points. And by radical, I will always mean the Jakobson radical, which is the intersection of maximal either left ideals or right ideals in our K-algebra. Obviously, you can also define radical for modules, and then it will be an intersection of all maximal left. I mean, of all maximal submodules. Yeah. So that's it. And if somebody doesn't know what a quiver is, but I suppose everybody knows what a quiver is here, then I have stated a definition if you really want to read it. One thing to keep in mind is that I will always assume that our quivers are finite and connected. Connectedness is a kind of not really that necessary of a assumption. Finiteness is, of course, much more necessary of an assumption. Yeah, that's one thing to keep in mind. I won't be assuming that our quiver is acyclic all the time. So that's something that will be underscored when it would have to be assumed. Yeah, so
just to make sure we're on the same page, by connected, you mean that between any two vertices there is an unoriented path, unoriented path.
Yes.
Undirected.
Yes. Yeah. The underlying unoriented graph is connected.
Sorry, I cannot resist saying this. Just give me 1 minute. Because it's the same as taking all hereditary subsets in a space of vertices, declaring them as a hereditary topology, and then connectedness is connectedness, the usual connectedness in the sense of this hereditary topology.
Yeah, I think so.
It's kind of quirky. Sorry for the interest.
No, it's okay. So I also here have a definition of a path algebra. If somebody doesn't know what a path algebra is in this whole workshop, it's just a algebra that's spanned by all paths in our oriented paths in our quiver, and it has a multiplication that's essentially defined by concatenation of paths. One thing to keep in mind is that the concatenation works in not a function way, but more of a pathy way, maybe. I don't remember, we were having a discussion about this. So essentially, if you have two vertices and, I mean, three vertices and two paths, then a path that starts with, I don't know, I can maybe write something if it's not clear quite well. I need a marker.
Oh, I don't know where you put those.
They were there. Well, good.
Yeah.
I was trolling. Okay. So just to kind of unwind this definition, of course, if we have two paths, then a concatenation of these two paths will be denoted by this guy. So for me, it was kind of, it's a kind of weird notation, and I wouldn't use it if I were to write, for example, a paper in this field, but I'm not maybe somebody that's actually actively working in this field. So, yeah. So some very close properties under our assumptions. The path algebra is always unitary and connected. It is finite dimensional if and only if our quiver is acyclic. And yeah, cyclic means oriented cycles in this case. And if the quiver is acyclic, then we have a nice formula for the radical, and it's just the ideal of paths of length at least one. And this is something that Professor Hayas was discussing, that there is a formula for the radical if the Q is cyclic. I will not have it here, but I mean,
I'm surprised it's not in textbooks, because
yeah, it's not in the text. I can tell you that much because I was going through the text. But there is a formula for the radical if we have a bound quiver algebra, because then it's very analogous to what's happening here. Yeah. So, and also there is this notion of a basic K-algebra. There are a couple of equivalent formulations, and I find the more simple one is that the quotient of the algebra by the radical is it has to be isomorphic to a product of our ground fields as a K-algebra. Yeah, and if we consider some cyclic quivers, then both of these statements about this radical being RQ and this quotient being isomorphic to some products of Ks, like the Theorem, you can consider just a quiver with a loop and a vertex, and yeah, it would suffice to produce a counterexample.
Just one question, what's RQ?
Okay, so it's the, oh, I can't go, oh, wait, now the arrows are working. Okay. So I can go back. Yeah, RQ is the ideal of arrows. So the ideal generated by paths of length, it's the ideal generated by edges. So as I said, it's just the linear combinations of all paths of length at least one. So if we divide by this ideal, then the KQ over the RQ is just a product of Ks, because it's just the stationary path. And maybe that's also something that, I don't know, it might not be clear. So in these path algebras, we obviously have paths of 0 length. So the vertices are also part of this path algebra. Otherwise, we won't have unitarity. So yeah. And admissible ideas, because I want to be talking about bounded quiver representations, and I need to talk about what ideas I allow myself to divide by. So these are the admissible ideas. And the definition might at first glance seem kind of, I don't know, for me it's like necessarily complicated. The best way to think about it is that these are the ideas that are generated by relations. So for example, if you have like a square diagram, then maybe you would like your representations to kind of have the commutative property, like a commutative diagram or something like that. So that would be a relation, but we allow more abstract relations, which are just linear combinations of paths that start and end at the same vertex. And the fact that these are exactly the ideas that satisfy this like two inclusion property is an easy exercise. Yeah, so these are the admissible ideals.
And by the way, please correct me if I'm wrong. The ideas which we will be talking about for compact algebras and Leavitt path algebras are not admissible, right?
So that's a question for people from Leavitt path algebras.
I remember us checking it once, and they are completely.
They're not admissible.
Not admissible.
Oh, I mean, it would make sense because of what I'll be talking about soon.
But this is an important point which we completely diverge. I mean, our starting point is path algebras, and then when you go to classification of this representation here of this Gabriel stuff, you really have to have this admissible condition, which is well, and it's,
Yeah, I mean,
it's immediately violated when they get there.
yes. So essentially, what these admissible ideas actually allow us to do is, well, yeah, I think it's clear that bounded quiver algebras, they are the quotients by admissible ideals. So I just wanted to have this definition. And yes, here in the radical is just the quotient of the radical of the ideal of arrows. So that's one way to kind of maybe attack trying to compute the radical of actual KQ without the division by I, but yeah, so maybe, I mean, it's a fun thing to talk about afterwards, this radical, but maybe not right now. So, okay, well, yeah, so this is kind of why the admissible ideas are kind of powerful. Well, we can have just a connected and finite quiver, and then the bounded path algebras are always unital, finite dimensional, basic, connected, and everything essentially works really nicely for them. So I suppose that Leavitt's path algebras are not of this type. Yeah, so that's why the ideas cannot be admissible, for example. but maybe that's something for me to learn in the future. So, yeah, the like kind of a cool feature of these constructions is that there is a Morita type equivalence, and maybe you can actually kind of correct me if I'm wrong here. So for me, Morita equivalence would be something like this. So the category of finite dimensional modules are equivalent. And
Not quite necessarily, but there was this.
yeah, okay. So I put Morita in quotes here. If somebody else wanted maybe had a different kind of Morita equivalence in mind. But yeah, so essentially what is actually this cool thing is that any finite dimensional algebra is Morita equivalent to this KQ over I kind of stuff. And actually I wanted to very briefly maybe talk about why this is the case. And to do that, I will be talking about idempotence. And this idempotence will be used throughout the whole talk. So we can always view our algebra as a module over itself. And then we can, since it is finite dimensional, we can decompose it into a finite sum of irreducible modules. And these modules basically form the set of indecomposable projectives in our category, or irreducible projectives. And since we have this decomposition to direct sum, we can identify all these idempotents that define this direct sum of A into submodules. And this set of idempotents that produce this direct sum decomposition into irreducible modules is called a complete set of orthogonal primitive idempotents. Or idempotents, and this is something that will be used throughout my talk, and so this set will be abbreviated to just a CSOPI. So that's what CSOPI means. Yeah, so in our quiver path algebras, in our bounded path algebras, the CSOPI, we have a very natural way to find such a thing, and it's just a set of stationary paths. And that's maybe if somebody is not convinced, and that's quite an easy exercise. So maybe a brief idea behind the proof of this theorem is that it actually can be done in 2 steps. And one step will be a Morita equivalence, and another step will be an isomorphism. So the first thing is that we can find a Morita equivalent to any finite dimensional algebra. We can find a basic algebra that's Morita equivalent to any finite dimensional algebra. And the second step is that, yeah, so basic is, actually here was the definition of basic. So we can take, so maybe if you want to have A instead of KQ, I will just say it like here. So basic is that you can take your algebra A and divide by rad A, and this is supposed to be isomorphic to a product of K's. So A is a K algebra, and yeah, and this is an isomorphism as K algebras. And yeah, this is for me a large K, but no, never mind. Yeah, so we first can approximate by a basic algebra, and then we can actually identify in this basic algebra a quiver and find an admissible ideal such that this algebra is actually isomorphic to this quotient that we want.
Now, please correct me if I'm wrong. This idea is definitely not unique for this isomorphism. But how about the quiver?
The quiver, it depends how you want to talk about it. I mean, the quiver is constructed using this set of idempotents,
Yeah,
but it's independent of the choice. And if you, I mean, the quiver is unique in the class of isomorphism, because if you take as A, just take KQ over I, then this quiver is just the underlying quiver. So you kind of end up in the same isomorphism.
just remember from the blue book that this is idea is nothing. You can have different ideas and the quotient will be the same. You go back the same.
Okay, you're correct because yes, the construction of the isomorphism requires some choices. And I guess that's why you would get different ideals potentially. But the quiver is, I mean, as far as I remember, the quiver is unique in the sense that you can take this A, you can construct the quiver QA, and you can construct the quiver of this KQ over I, and you get again the same quiver. So you couldn't have had a different quiver from the beginning. Yeah, and both of these constructions are defined using these CSLPIs, but they are both independent of this choice, well, after an isomorphism. So I have a very brief idea why this what are these constructions. So essentially, what's the problem with non-basic algebras? It is that when you look at your decomposition into these irreducible modules, so you have like this E1A plus plus some E, say NA, then if all of this would be pairwise and isomorphic, then actually it would be basic. So the idea is to kind of delete those modules that are pairwise isomorphic from this. And the construction follows essentially what I have just stated. So we just pick a subset that has pairwise and isomorphic modules generated by this idempotent, and we can generate a basic algebra using any idempotent. So this is the algebra that we are generating, and the equivalence of categories is using, of these two categories is using some, well, quite natural functors. It all obviously requires some checking that it's an equivalence of categories, but I'm not going to delve into that. Yeah, so that's how you construct kind of this basic algebra.
Can you remind me what CSPO?
Yeah, so it's this set of, well, it's the set of complete set of orthogonal primitive idempotents.
Of course.
So the idea, I mean, the idea is that you have your algebra and you you decompose it into some of irreducibles, and these idempotents are these sets essentially. They kind of correspond to decomposition into reducibles. Yeah, so this is this first thing, and the second thing is to construct a quiver having a basic algebra. So this is the kind of the construction. So you can take your sets, well, of idempotents, and you can define a quiver using these relations, and maybe as a little sanity check, I encourage everybody to maybe think about what happens if we actually have the scenario that I described. So we have an A equal to KQ over I. So then we know that the radical is actually the radical of arrows, but divided by I, right? So if we actually look at the set of edges, so our set of idempotents is going to be the set of stationary paths. So the set of vertices from our quiver. So QA naught kind of is equal to just Q naught. And if you look at the edges, then actually what happens here is that you, well, you take your idea of arrows and you divide by the idea of paths at least of length at least 2. So actually, if you want to look at the edges, say from I to j in, well, these are some elements in Q naught, then you would look at these products. Okay, so if you multiply by stationary paths from the left and from the right, then we actually look at only paths from I to j, and we look at things of length at least 2, but we kill things of length at least, I mean, we look at things of length at least 1, and we kill things of length at least 2. So you get the edges. So that's kind of maybe a little motivation why this construction is good, I would say. So yeah, I hope that everybody is kind of convinced by it and that it actually works. In order to construct the isomorphism, we have to construct some surjection and prove that the ideal of this, I mean, the kernel surjection is admissible. And this is a kind of just a technical check. It's not that interesting, I would say. This projection is mapped in like the most, obvious way kind of possible. So we know that elements of QA naught are actual elements of A, and we have to somehow lift elements from here to our A. So we just pick some lift, and that defines a map. And yeah, that's kind of the idea behind this construction. So I don't know if there are any kind of questions about it, but I suppose not. It's just some, like getting the rest of the proof is just some technical kind of playing around with properties of these radicals and stuff like that.
This is A of quiver, right?
No, it's not. I mean, it's not called like that. In this blue book, they call it the ordinary quiver.
Ordinary.
Yeah. Because it's supposed to be different from different quivers which are not ordinary, apparently. I mean, it's called ordinary in this blue book. That I can tell you. Yeah. So quiver representations. I wanted to give like a very kind of brief overview of what they are. Well, given a quiver, we can define a free category on this quiver, and quiver representation are just functors from this free category to vector spaces. I hope that is clear for everybody how this works. And if you're not convinced, then what actually happens is that the quiver representation is just a way to take some quiver like this, for example, and well, we have to put some vector spaces over our, say, over our vertices. So we put some vector spaces over the vertices, and I somehow made different way notations here, but yeah. And we also have to put some linear maps as the edges. So we have some up here, some up here, and here, and here. Okay, and morphisms of quiver representations are natural transformations, because it's a category of functors. So these are just maps like from, between the fixed vertices that are supposed to make everything that can be commutative. That's the very brief explanation. And yeah, we will call a quiver representation finite dimensional if it factors through an embedding of finite dimensional vector spaces inside of vector spaces, or in other words, if every like vector space over any vertex is finite dimensional, then our quiver representation is finite dimensional. And lastly, bounded quiver representations. It's kind of a mouthful to describe, but it's very easy to kind of give as an example, right? So say that we have maps F1, F2, F3, F4. Then, well, what we can do is that we can have a relation. For example, we can have a relation that F3, F4. Okay, so if we have a quiver, the underlying quiver would look like this. Okay. So maybe I will just also do this, and I will do this. Yeah. So, we can have some sort of relations. For example, if you want the commutative relation, then it would look like E3, E4 minus E2 or E1, E2 is 0. So a bounded quiver, a quiver representation that's bounded by this relation is just, well, it's a representation, so it's something like this. And we have to evaluate this relation on our maps. So this would translate to a condition of our function. So this would mean that F3, F4 minus F1, F2 is 0. So, and yes, any admissible idea is generated by some finite amount of relations, then a representation bounded by an admissible ideal is just that we just impose all of these relations on our representations. So I also hope that this is like not confusing at all. And obviously there are equivalences of categories. So the representation of quivers correspond to modules over the Bach algebra, and the representation of bounded representations of quivers correspond to bounded. They correspond to modules over the bound quiver algebras. And if we descend to finite dimensional modules, then we obtain finite dimensional representations, and everything works as one would hope to. Yeah, and this is with, I think, like no assumptions on the quiver besides maybe being finite. Because in order to have this commutative diagrams, I mean, finiteness is certainly necessary, and I think we don't need any like other conditions. Okay, so I won't really delve into the details on that because I can clearly see that I'm running out of time. And so maybe a bit about representation theory. So this is also something that's completely different when trying to go into the realm of, for example, Leavitt's path algebras, as I have understood it. So in the realm of bounded quiver representations, actually, in the irreducible projectives and injectives and simple modules are very easy to describe. They are immediate, and yeah, that's like not an issue at all. But as I understand it, it's completely different in this Leavitt's business. Yeah, so I'm kind of talking to the audience that's experts on the Leavitt algebras. Yeah, but in order to describe the projectives, well, we have this decomposition. So actually, since A is finite dimensional, then this decomposition gives us a full list of irreducible projective modules. And actually, we can dualize it into also a list of injective irreducible modules. And the only thing that's, well, actually, we have to like define something is the simple modules. The simple modules are, well, they are very simple. We just put the field over a vertex, and they put zero everywhere else. And these are simple, and as it turns out, these are the only simple modules. Yeah, and if we try to, for example, go to cyclic quivers, but without dividing by an admissible ideal, then it is very easy to produce very different simple modules. So, yeah, and if we go even further into some other algebras, then yeah, the story is much harder. So yeah, this is the kind of the base point of this representation theory. And yeah, I wanted also to talk about the Cartan matrix. So this is quite a useful gadget. So obviously, when we have a quiver representation, then we can have the so-called, I mean, the dimension vector. So we can just take dimensions of everything that lies over every vertex and put it together, and we have the dimension vector. If we, just for simplicity's sake, assume that our vertices are numbered, which is, I wrote, not a hard assumption to we can write everything as just like usual vectors and matrices. So we can define the Cartan matrix, and this is this matrix. Obviously, this might not be like immediately clear why would we want this matrix, but and also even if somebody, for example, knows why this matrix is useful, it might also not be immediately clear why it's called Cartan matrix, which has the same name as the Cartan matrix in Lie algebras, for example. And as it turns out, there is a like connection between all of this, between these two topics, which maybe I will talk about.
Just a stupid question. What are these P1, PI?
Yeah, so these are these projective modules.
Ah, okay, fine.
Yeah. And also there are these injective modules, which are just the duals. And obviously, if you take this Cartan matrix, then the columns are the dimension vectors of the projectives, but at the same time, the rows are the dimensions of the injective modules. And yeah, as it actually turns out, because we have a matrix whose columns are dimensions of all of our irreducible projective modules, and probably it can be useful for some homological algebra. So this is why we can define this object, which is the Euler form of a quiver or a bounded algebra. And yeah, also, by the way, I will be using A, and A will always be just a bounded quiver algebra. And yeah, just a heads up. So we can define this form, which is defined as the Cartan matrix. And Well, because computing X groups requires, for example, computing some projective resolutions, then it might not be too weird to think about this result that actually when we plug in some dimension vectors, then we actually get like this Euler characteristic of say, extension groups. And to completely like give a proof of this, I won't give a technical proof of this. Well, you actually do some homological algebra. So you consider your modules and you well, in the blue book, they do it by induction on the projective dimension of I think we have to do it on M. No, on N. We have to do it on the contravariant. So yeah, that's. But for me, for example, this is a very kind of nice result, especially because if we, for example, look at acyclic quivers, then this Euler form has a very kind of easy compute form, using only like the information about vertices and edges. But in general case, if we also divide by some admissibility, then this form is kind of harder to compute, but it's completely computable. And it's like, it's very hands-on. And also there is a thing called the quadratic form, which is just a quadratic form of this bilinear form. And yeah, you can try to do some, let's say, the algebra with this quadratic form. You can look at the roots of this guy and try to compute the Weil group of like reflections with respect to the symmetric bilinear form that comes from this form. And this connection with roots of and this Weil group is I would say, one of the like central, maybe not central, but it lies in the heart of the Gabriel theorem, because you essentially show that the Weil group that's defined by this quadratic form is finite, well, only in the case of quivers which have the underlying or unoriented graph being a Dynkin graph. Yeah, so like Gabriel's theorem is, for me, it's very much interesting from this point of view, but I hope I will be able to maybe get to it by the end. So yeah, I would like to talk about the Auslander-Reiten theory. So the objective of the Auslander-Reiten theory is to describe, I don't know how we'd call it. I think you would call it, I mean, in the book, they call it an approximation of the whole category of modules over like a fixed basic finite dimensional algebra. For me, it's like kind of maybe like a spanning, like a minimal spanning graph of a module. So if you kind of appropriately extend everything, then you get the whole category of modules. So if you want to talk about the representation theory of some algebra, then you are probably mostly interested in talking about irreducible modules, because since we are over the like algebraic equals field, then we can always decompose stuff into irreducibles, and probably we'll be fine and won't get into some weird kind of not, how do you call it, non-unique decomposition kind of businesses. So we want to focus on irreducible modules. And the next problem is to describe the homomorphisms between irreducible modules. And yeah, to describe every kind of every possible home set, it is quite a big challenge. So what you can do is you can also define an irreducible morphism, which is supposed to be a building block of all other homomorphisms. And so this is the definition of an irreducible morphism. And as it turns out, if we look at only these guys, so not sections and not retractions, so they don't have any sort of inverse, and also they don't factorize into something that also does not have any sort of inverse.
Can you provide section and retraction?
Okay, so now I want to, because it's going to be having a left or a right inverse.
That's what it means.
Yeah. So if you have well, if you have a fiber bundle, then a section is a map in this way, such that if you go like here and like here, you go to the end. Right? So that's a section, and refraction is the other way around. So that's this thing, and yeah. So as this proposition, this truly is a building block all homomorphisms. Well, this is what this proposition is about. So we can just take compositions and sums, and actually in this way we can obtain any sort of homomorphism between two irreducible modules. I think this is not true for not irreducible, and there are also obviously isomorphs. So yeah, because I mean you can't really get an isomorphism through irreducible maps. Yeah, so the Auslander-Reiten quiver is this kind of approximation of our category of modules. So the vertices would be the irreducibles, and we want the edges to be, well, we want the edges to be the irreducible morphisms, but these themselves don't fit into a vector space. So in order to fix this, there's this thing called the irreducible space of irreducible morphisms, and this is a quotient of radicals. So what actually is written in this slide is something that I won't be really defining. So these are the categorical radicals. So if M and N are irreducible, then actually this rad Mn is just a set of non-invertible maps. And what this guy actually is, you can think of it kind of as as the set of things that are well, they are kind of like non-invertible maps, which are factored through two non-invertible maps. It's kind of not really true what I'm saying, but it's the best approximation that I can give in this amount of time. So it's...
Sorry, Mateusz, is A still finite dimensional or not?
Yes.
It is.
I mean, okay, for this definition, it doesn't have to be. But what we will do is use this quiver for finite dimensional A. But you can do it like this is just a definition. Yeah, so what's actually nice about this quiver is that there's this thing called Auslander-Reiten translations, which I do not have time to define. But they are the kind of symmetries of our quiver, and they are actually used to kind of try to compute this whole quiver, because like what's I think remarkable about this thing is that for finite dimensional and representation finite algebras, this quiver is almost algorithmically computable. Like you can sit down and compute the whole quiver in a finite amount of time. Maybe let's say that way. Yeah, so this is like quite remarkable about this thing. I won't really get into the detail, besides the fact that in order to compute all of those irreducible morphisms, we use this thing called the almost split exact sequences. So this is an exact sequence, and this is an exact sequence such that the ends are irreducible. The middle part does not have to be irreducible, but the maps are irreducible. So actually, these sequences kind of give you everything that you want to compute this quiver. Yeah, and like there's this big thing of the Auslander-Reiten theory, and it states that if you have a non-projective irreducible module, then we can create such an almost split exact sequence, and if we have a non-injective irreducible, we can also create such a non-split exact sequence. It's kind of non-trivial that such a sequence exists, but yeah, I have to kind of speed up. So there's this functorial approach, but this is something that Professor Maszczyk wanted me to say, but I don't really have time for it. But if you want me to just throw you a definition, then actually almost split exact sequences correspond to minimal projective resolutions of a simple module in the category of functors. So we are actually computing some projective resolutions just in a higher category in some sense when we try to compute these sequences, because in the heart of computing these quivers is the computation of these exact sequences. yeah, so this is like the definition. If you want, it will be on the slides. Yeah, so why are this? Oh, okay, I have to finish soon. So why are these almost split exact sequences useful? Well, they are useful because actually, when we want to talk about the arrows in our Auslander-Reiten quiver, then we only really have to look at those sequences, because, like I said, in this middle part E does not have to be irreducible, so it can decompose into some irreducibles, and as it turns out, every single map that appears between irreducibles, like from M into any irreducible direct summand of E, is a arrow in our quiver, and for non-projective M's, right? And for non-injective N's, the same thing holds true. And if we want to talk about, if you want to talk about projective modules, then actually we only have to talk about direct summands of the radical, and these are all the arrows that are going from into our projective modules, and to describe all arrows going out of injective modules, it's a dual kind of notion. Yeah, so we only have to really compute these non-exact, almost fit exact sequences, and they are completely computable using this Auslander-Reiten translation business. So yeah, just to maybe kind of state these like bigger results that are used, that are kind of proven in many different techniques. Auslander-Reiten theory is kind of included in these techniques, is that we can actually, in this whole category of like these basic finite dimensional algebras, we can find hereditary algebras which have the global dimension bounded by 1, and as it turns out, these are exactly the KQs with Q being asymmetric. And the fact that such a KQ is hereditary is kind of easy to do. In order to prove the kind of converse, it's a bit harder, but it's doable. It's kind of, it doesn't use heavy machinery, I would say that much. Then there is this Brauer-Thrall conjecture, which I have stated only the first conjecture. There's also the second conjecture, which is kind of, it's more general, but yes.
So about this first theorem. So imagine I don't want this algebra to be, let me say, and that is that this QA quiver finite. So I don't really hereditary. So then can I have, but it's basic, okay? And it's basic but not hereditary. Then can I have a case where this quiver QA is not finite?
I mean, you would have some problems because if the quiver is not finite, the algebra is not unitary, for example. So we will be talking about, like, you have to kind of loosen up many assumptions.
But it would still be basic or no?
Would it still be basic?
Yeah. I'm just
Yeah,
curious, but it's A is basic.
Okay,
QA is
well, if Q is not finite, then okay, so I would have to like confront one thing about basicness. If it depends whether the infinite product of case is a thing that you can allow, and that I don't know. I think, I mean, in that sense it would be basic, because if you divide by the radical, then it would be just an infinite product.
Yes.
Of case. But if you want to talk about, is this question like completely not about these results, right?
Yeah.
Okay. So
I
think, for example, in this book, they assume that the product has to be finite. In that case, the quiver has to be finite.
Okay.
That's force. Yeah. So okay. So I don't have time to talk about maybe generalizations that I wanted to talk about, but yeah, the second, maybe just that's a few last comments. So the second thing actually uses irreducible morphisms, because you can analyze, for example, lengths of modules, and you can analyze sequences of irreducible morphisms, and how actually there is something to, like, some results to prove there about the lengths of these sequences of irreducible modules. And what you can prove, and this proves this conjecture, is that actually, if you have this Auslander-Reiten quiver and you have a connected component, in this quiver such that the lengths of all modules in this component are bounded uniformly, then actually, first of all, it has to be finite. The connected component itself has to be finite. And secondary, the whole quiver has to actually be this one connected component. So there is a stronger theorem that proves this conjecture. And yeah, Gabriel's theorem is a very technical result, and it uses many, many different tools that I haven't talked about here. Like, I think it uses tilting theory. It uses those roots of the, oh, I have a mistake.
Drinking quiver.
Yes, sorry about it. But maybe one thing that I have read about this Gabriel theorem is that Katz has made some generalizations in the sense that we can try to talk about different quivers which are not acyclic and what happens then. And can we, for example, say something about some representations? And as it turns out, there is some results regarding this Euler quadratic form and its roots. And but you have to go for example, into Kac-Moody algebras and stuff like that. So, like for me personally, it was interesting to find that, but I don't know if that is the same for you. I just wanted to give you like a fun fact about it. So yeah.
So your representation finite, what does that mean?
So there are a finite amount of isomorphism classes of irreducible modules.
Okay, you reduce. Yeah.
Yeah, you cannot. Yes, finitely many irreducibles.
Yeah. The primitive spectrum.
Yeah, you can ask, for example, what happens if you try to realize some of these conditions. And yeah, Katz was working with some generalizations when you lose acyclicity. And apparently there is something to read about that. So yeah, that's all from me. So yeah.
Very much. Are there questions or comments for Mateusz? Online.
Wait, there is something in chat, and there are 6 people on Zoom. Will the recordings be available for rewatch? Rosbeth?
Yes.
Yes.
Upload that and then send an email. One. The center has the school has a channel, so we're gonna upload there. Please.
Okay.
All right. So now we can swap. Oh no, now the break, right?